Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology under the LG University. As we are already discussing about the digital logic design, where the fundamentals of digital logic design started with the numbering system, then converting one numbering system into another numbering system, as well as we have to define a different kinds of codes that we are learning with respect to make the communication or transfer the information from one device to another device, right? Now based on that, what kind of circuit parameters, a kind of development or build of digital circuits that we need to understand. So there are certain fundamentals based on different logic blocks of a digital circuit we need to understand. So we'll start with, first is the introduction of logic. What is logic? So every day, our routine life, we always follow kind of different logic, like something that we have to add, something that we have to subtract, or we have an option yes or no, or we have a do not have any option yes and yes, like that way. So based on that, we define a logic in terms of the digital circuit. Is the digital logic is the underlying logic system that drives the electronic circuit board design, right? So based on this electronic circuit board design, we apply plus 5 volt, that means a binary digit 1. If we apply 0 volt, that means binary digit 0. Based on that, we define a specific logic. So ultimately your digital system will process 1 and 0 as per the desired output. So they are going to process that 1 and 0 based on something, and that is called the logic. So here the digital logic is manipulation of binary values through printed circuit board technology that uses circuits and logic gates to construct the implementation of computer operations. So we have a different computer operations like arithmetic operation, logical operations, and all those operations we can do with the help of digital circuits. In a scratch level, they are the electronic circuits. So first we try to understand, based on those logic, what are the different circuit parameters or logic blocks that will simplify the digital operation. So we'll start with, see, these are the equipments where you can see lots of the switches, displays, then you have a wiring, and all those wiring carry a specific kind of information, and those information in a binary way, it is a 1 and 0. So based on that, we have a different kind of logical parameters or operators we consider as a AND. So we normally use that the sign of AND is double AND, same way, or not. So these three are the basic logic functions. Like, so in our everyday life, if we have an option a or B, we can choose either A or B. That is a kind of ORing function. We have a and B, so it must be a both parameters you have to consider. This is like a ANDing operation. Same way, we do not have to consider any option like A and not A, so it's kind of not operator. So the basic operators are like AND, OR, and NOT. And the combination of AND, OR, and NOT, you have a universal logic operators like NAND and NOR. Now based on that, we have some exclusive operations which we consider as a XOR and XNOR. So let's say one by one we consider those are the logic gates. So we'll first start with the NOT gate. So you can see here NOT gate. NOT gate is nothing but the single input and single output gate, right? So the gate is also known as an inverter, and because it performs the inversion of applied binary signal, right? So if you're applying one to NOT gate, it will give you the output is 0, and if you apply the 0, it will give the output in form of 1. So you can see the symbol of NOT gate where you applied 1, and the output Z is equal to you can see the symbol of NOT gate where you apply A and you'll have output of A bar. So once you apply 0, you'll have a 1. Once you apply 1, you'll have a 0. So you can see the output A with respect to output, you can see the input A with respect to output Y or Z You apply 0, you'll have a 1. You apply 1, you'll have a 0. Based on that, we have a further discussion on an AND gate. So this is kind of ending operation. Matlab, ending operation means both option must be required to choose. So here the Boolean operator which gives the value 1 if only all the operands are 1 and otherwise the value becomes 0. So that means this must be operated with both the inputs are become 1. So this is what the symbol of AND gate, where A and B both the inputs are 1, then and then Y becomes 1. Otherwise rest of the all the positions the output must be 0, right? You can see the Boolean function of AND gate, which is Y is equal to A into B, where you can see the truth table where A and B both are 0 0. So Y is equal to A dot B, 0 into 0, you'll have output is 0, right? Likewise 0 1 output is 0, 1 0 output is 0, but both the inputs 1 1, then and then you'll have output is 1, right? So based on that, again you have one more basic gate which is called the OR gate, and that will give you the function of ORing. That means they choose between two input. So the logical operators which gives the value of 1 if at least one operand or one input has the value of 1. So otherwise rest of the positions output are 0, right? So this is kind of ORing function, and this is the symbol of OR gate where you have a two inputs, A and B, and the output Y is equal to A plus B. So in Boolean function Y is equal to A plus B, that means either value is 1, the output is 1, right? So you can see the truth table where A and B both are 0 0. So Y is equal to A plus B, that means 0 plus 0 output is 0, right? But again in a binary system, again in a digital system, if you apply 0 and 1, so Y is equal to A plus B, 0 plus 1 output is 1, right? So this is like a digital operator or so 1 0 output is 1 and 1 1 output is 1, right? So this is what kind of basic three gates like AND, OR and NOT, right? Now based on whole our process is always ending either ORing or NOT, right? So with the combination of this AND, OR and NOT, we'll have a one more combination we can define as a NAND. Now NAND is nothing but the AND plus NOT. So NAND is nothing but the AND plus NOT. So this Boolean operator which gives the value of 0 if only all the operands have the value of 1. So if all operands have the value of 1, otherwise the value is otherwise has the value of 1 equivalent to not AND. So this is nothing but the combination of AND gate and NOT gate. So once you apply A B to AND gate, it becomes A dot B, and further it applies the Boolean function of NOT. So A dot B bar, right? So that's what its Boolean function is A Y is equal to A dot B whole bar. So it's completely a reverse of or complement of AND gate, where 0 0 it becomes 1, 0 1. So 0 dot 1, A is 0, B is 1. So 0 dot 1, the output is 0, zero's complement output is 1. So 1 0 1, but 1 1, see exactly it's a 0. So this is exactly the NOT function of AND gate or complement of AND gate. Now similarly if you consider the NOR gate, the NOR gate is nothing but the OR plus NOT. So it's a plus B, and then you have to apply the NOT. So it's a plus B bar, right? So that's what the Boolean function of NOR gate, where you can see there are two inputs A and B. So if you consider this particular truth table, you can see here with the NOR gate. So input A, input B, both are 0 and 0. So 0 plus 0, answer is 0. Zero's complement answer is 1. So you can see this is exactly a complement of OR truth table, where if your input is 0 and 1, see 0 plus 1 output is 1, 1's complement output is 0. So for NOT gate, 0 1 output is 0, 1 0 output is 0, 1 and 1 output is 0. So that's what exactly a component exactly the complement of OR gate you are going to get in form of the NOR gate, right? So you have a three basic gates, AND, OR and NOT, two universal gates, NAND and NOR. Now why they are called universal gate, that we will discuss in our future session, right? So if you further discuss about the some of the exclusive gates, like you can see here the XOR gate, where this becomes the XOR, this becomes the exclusive logic or exclusive operator. So here the output of XOR gate is high only when exactly one of the input is high, right? High or 1. If both the XOR inputs are zeros, if both the inputs of this XOR gate are 1, the output of the XOR gate is low, right? So any of the input is 1, output becomes 1. If both the inputs of zeros or both the inputs are 1, then and then the output becomes a 0. So this is one more defined logic, and this is a kind of exclusive operator. So you can see this is a XOR gate. So this is a symbol of XOR gate where there are two inputs A and B, and you will get your output is nothing but A bar into B plus A into B bar. In a way, it is defined as A XOR B. You can see here A XOR B is defined like that way. But in a Boolean function, it becomes A bar into B plus A into B bar, right? You can see the truth table where if you apply 0, 0, output must be 0. If you apply 0 and 1 or 1 and 0, see one of the input is 1, so output becomes 1. That's what the exclusive OR gate, right? If both the inputs are 1 and 1, output becomes 0 because it follows the Boolean function of A bar into B plus A into B bar. That's what the exclusive OR gate, right? One more, if you talk about the exclusive logic gate, XNOR, which is nothing but the complement of XOR, right? So whatever you observe or whatever you realize during the XOR gate, that is exactly the complement you can see in the truth table. So you can see the symbol of XNOR gate. And what is XNOR gate? The output of XNOR gate is 1 when both the inputs are 1 high or both the inputs are 0. If either one of the input is 1 high, the output will be 0, right? So in other words, both the inputs should be in a same logic level for the output to be 1, right? So you can see this is the symbol of XNOR gate where it has a Boolean function of y is equal to a dot b plus a bar into b bar, right? So this is nothing but the complement of XOR gate, and you can realize the truth table where if a and b both are 0, 0, you can see the output is 1. But if A and B either is 1, if A is 0, B is 1, the output is 0. Same way, if A is 1 and B is 0, the output is 0, right? And both the input is 1, 1, see the output is also 1, right? So based on that, we learned about all the logic gates. If you talk about the summary, you can see the AND gate. AND gate is nothing but the symbol of AND gate and the description of AND gate that we have already discussed. And if you talk about the kind of Boolean function where x is equal to a dot b, same way for a OR gate, you can see the symbol and x is equal to a plus b. NAND gate, see x is equal to a dot b whole bar, right? With NOR gate is x is equal to a plus b whole bar. XOR gate is x is equal to a XOR b, that means a bar b plus a into b bar. XNOR gate is like x is equal to ab plus a bar into b bar, and NOT gate it's an inversion. That's where you apply a, you get a bar, right?
The basic idea behind this Boolean algebra is a kind of mathematics, is just to reduce the number of gates, just to realize and reduce the Boolean functions, right? Thank you, dear students.